We're going to see now an alternative approach to building confidence intervals. I have to say that building confidence intervals is probably a better way to get a sense of what the true population parameters for your underlying distribution might be. But in many instances, we just have the machinery of hypothesis testing behind us, and so we often will use hypothesis testing instead of building confidence intervals. There are issues associated with hypothesis testing, especially when it comes to the p-value and what it might mean. Let's start with a simple scenario, a scenario that discusses claims and suspicions. When you do statistical analysis, you basically have to be a very suspicious person. So in this scenario, person A, they claim to have a fair coin. But for some reason, person B is suspicious of the claim. They actually think that the coin is biased in favor of tails. So person A hands over the coin to person B, who proceeds to flip the coin 10 times. Because they believe the coin to be biased in favor of tails, they would expect a low number of heads in that sequence of 10 flips. And they would attempt to use that as evidence against the claim. Of course, before the data has been collected, a claim is just a claim, it's just a belief, right? I mean, it's conceivable that the data that person B will collect by flipping the coin 10 times will not be evidence against the claim of the coin being fair. We'll have to see what the data says. So our random variable here will be x, the number of heads you flip in n trials, in this case 10 trials. Let's say that person B did flip the coin 10 times and she observed 4 heads. So her x is equal to 4. This is less than you would expect for a binomial random variable with parameters 10 and 0.5 if you had a fair coin, because the expectation for that random variable would be 5. You would expect to see 5 and you see 4. The results that you observe in this sequence of trials, they're more in line with the coin being unfair and having a probability of flipping a head to be 40%, 0.4. But does this data really constitute evidence against the claim that person A makes, meaning that the coin is fair? The probability of flipping a head is 50%. I mean, if you were to flip a coin 10 times independently, you wouldn't be that surprised to find that 4 of these tosses resulted in heads, right? 4 is still pretty close to the expected value of the random binomial variable with parameters 10 and 0.5. If you compute the probability that x is actually equal to 4, which is the same in the binomial expression, you will replace x by 4, and n by 10, and p by 0.5. If the coin was fair, this value here is approximately 20%. And 20% of the time, when you flip 10 coins, you would expect to see 4 heads if the coin is fair. So the fact that you saw 4 heads here isn't really that strong of an evidence against the coin being fair. I mean, even the expected value, x equals 5, only draws a probability of 25%. It's not that much more. So in the probability density function, or probability mass function, because we're talking about a discrete random variable, x equals 4 is this red column here, and it's not entirely unlikely. In fact, it's one of the 3 sort of main possibilities, 4, 5, and 6. Now, the way that we've worded the sentence here, it would seem that there is no evidence against the claim that the coin is fair. That's a very important wording. If you flip a coin 10 times and you observe 4 heads out of 10, that is not evidence against the claim that the coin is fair. But it doesn't mean that the coin is fair. Right? We did not reject the claim that the probability of tossing a head is 0.5, that the coin is symmetric, that it is fair. But that doesn't mean that the probability of flipping a head is 50%. accepting a claim or not rejecting a claim is a very weak statement. To give you an idea as to why that would be the case, let's say there's a third person in this scenario, person C, and he claims that the coin from the example above actually is biased, and the probability that you would flip a head is only 30% as opposed to 50%. He builds his binomial distribution with parameters 10 and 0.3. He observes what person B has flipped, and she has found 4 heads. So under his scenario, the probability that X would actually be equal to 4 is actually 22%. Right? In this case, you would still get the binomial expression, except the values of P and 1 minus P would be different than the ones you had before. But this probability is still, roughly speaking, 22%. Right? So that is not enough evidence to reject the claim that the probability of flipping a head is 30%. You can make a fair amount of counterclaims. You can't reject either one of these claims based on the data that you've observed. So not rejecting a claim is a weak statement. Rejecting a claim is a very strong statement. To be able to flat out say, no, the coin is biased, or no, it is biased but not with this bias, that's a strong statement. That's something that requires more evidence. Weak statements can be made with weak evidence. Strong statements require strong evidence. I'm going to focus as well on a peculiarity of the wording. Instead of saying accepting the claim here, I'm actually going to spend a fair amount of time talking about not rejecting claims. That's specific to the language of hypothesis testing. We have to be careful about what term we're using. Now let's say that person B is going to flip the coin another 90 times. So originally 4 out of the 10 flips were heads, and now we flip it another 90 times, and at the end of the experiment we have 100 tosses. Let's say they're all independent from one another. You get a total of 40 heads. So now the question is that the same evidence as before? When you flip 4 heads out of 10, when you flip 40 heads out of 100, in both instances you get an estimate for the probability of flipping a head of 40%. But are both of these experiments carrying the same evidential weight? Does this new series of 90 flips provide you with any evidence against the claim? And if so, by how much? So now we have a new random variable y, and it counts the number of heads when you run 100 trials, assuming that the coin is fair. Y equals 40 is smaller than what we would expect because the expectation of that random variable is 50 n times p, assuming the claim of the coin being fair is true. Just as x equals 4 was smaller than what you would expect because the expectation was 5. Y equals 40 is actually more in agreement with the probability of the head being flipped, the bias being 40%. But now, if you look at the probability mass function of the y variable, that event does not actually lie in the probability mass center of distribution. Let me flip back a few slides here. The probability that x equals 4 was basically in the center. This is where most of the probability is found. If you draw the corresponding probability mass function for the y variable, you will see that the probability that it's equal to 40 here is actually not in the center. It's a pretty small probability. This is not where the mass of the probability is found. It falls in the distribution tail to the left in an area of lower probability. The actual probability that you would observe 40 heads out of 100 tosses, assuming the coin is fair, is only about 1%. It's a substantially smaller probability than the one we had when we were looking at the probability of observing 4 heads out of 10 tosses. If the coin is fair, the event that you would observe exactly 40 heads is actually quite unlikely. Whenever you observe values in the lower tails or the upper tails, depending on the situation, that provides you some evidence against the claim. The question that you have, though, is how do we quantify this evidence? I mean, if you think about it, the probability that y is exactly equal to 40 being approximately 1% would seem to suggest that it's very unlikely that the coin is fair, because we're very unlikely to actually observe this. But even if you take the most likely case, the probability that y should be equal to 50, that is only about 8%. That is not super likely either. When values are further down the left tail or further up the right tail, that gives you evidence, as we said, against the claim of the fair coin. We'll actually use the tail area. We'll say, well, hang on, what's the area of this little tail here from 40 onwards? What's the probability that y would be 40 or smaller than 40? The smaller that tail area, the greater the evidence against the claim, based on the data that we've observed. So if you only have 4 heads out of 10 tosses, the evidence is the p-value. The p-value is the probability that your experiment of 10 tosses would yield what you've observed in terms of the number of heads or fewer heads. 0, 1, 2, 3, or 4. Assuming the claim is true, assuming that the coin is indeed fair. So the probability that x should be smaller than or equal to 4 when x follows a binomial distribution with parameters 10 and 0.5 is about 38%. What we're saying here is that the area, these chunks here in red, about 38%. That is not very unlikely. That does not provide a lot of evidence against the claim that the coin is fair. But if you do the same thing with this new distribution, the probability that y would be smaller than 40, including 40, if y follows a binomial with parameters 100 and 0.5, is actually quite small. It is only 0.028, about 3%. If the claim was true, that the coin was fair, the chances of you observing 40 heads or fewer is only 3%. The fact that you're observing something which is so unlikely makes us question the validity of the claim about the coin being fair. You would only see evidence that extreme or more extreme about 3% of the time. So the p-value is the area of the tail of the distribution of the random variable of interest under the assumption that the claim is true. And if you have a small p-value, the area of the tail is very small, which means that your results aren't very likely, assuming that the claim is true, which provides you with evidence against the claim. Well, in the vernacular of hypothesis testing, the claim is what we call the null hypothesis. We denote that by H null or H0. The suspicion is called the alternative hypothesis, and it's denoted by H1. I said the alternative hypothesis, but we've seen that you can have multiple suspicions. Like one person suspected that the coin was biased with bias 0.3, but another person could suspect that the coin is biased with bias 0.4. These are not the same suspicions. They're different alternative hypotheses. Nevertheless, in general, you pick one specific alternative hypothesis, and we call that H1. Later, we'll see what types of alternative hypotheses exist. The random quantity that you use to measure the evidence, we call that a test statistic. You need to know this distribution, assuming that the claim is true, assuming that the null hypothesis holds. And the p-value that quantifies the evidence against H null, and it's typically given as a probability that your test statistic would be smaller than some quantity or greater than some quantity. We'll do plenty of examples. In the coin tossing situation that I've just described, the null hypothesis is that the coin is fair, which is to say that the probability of flipping a head is 50%. The alternative hypothesis, because people believe that the coin was biased in favor of tails, is that the probability of flipping a head would be smaller than 0.5. If the coin is tossed n times, the test statistic will be the random variable which measures the number of heads in n tosses. So, as we've seen, if n equals 10 and x equals 4, the p-value is the probability that the test statistic would be smaller than what's observed. You've observed 4 heads in 10 tosses. That probability is 38%. If you assume that the null hypothesis holds, which is to say that x follows a binomial distribution with 10 tosses and a chance of flipping either one of them being 50%. That's a very large p-value, and so we do not have a lot of evidence against the claim of fairness. It is completely reasonable to see 4 heads and 10 tosses if the coin is fair. If you toss the coin 100 times and you observe 40 heads, then the p-value is the probability that you could observe 40 heads or fewer if your random variable follows a binomial distribution with 100 trials and a probability of success of 50%. In other words, assuming that the null hypothesis is true, and that p-value is very small, about 3%. It is unlikely that you would observe that. And so we conclude that it's probably highly likely that the claim is not valid, that the null hypothesis does not hold. Now you might say, it's easy, just run more experiments and I will always be able to prove that the claim is not valid. But if the coin was fair and you ran 100 trials instead of just 10 of them, you probably would not be seeing 40 heads. You'd probably be seeing like 48 or 47 or 53. And these are all likely outcomes of flipping a coin 100 times if the coin is fair. How small does the p-value need to be before you can conclude that there's not enough evidence to dispel the claim, or that you have enough evidence to reject the claim? I said 38% was not that small. What constitutes compelling evidence? There's no easy answer to this question. It'll depend on many factors, including what the price is for making an error, for falsely rejecting a null hypothesis which is true. There's 2 types of errors. For this one here, we'll look at what we call the type 1 error, alpha. That's the probability of rejecting the null hypothesis when the null hypothesis was true. If the p-value is smaller than this probability, then you would reject H null. If the p-value is larger than this probability, then you do not have enough evidence to reject the null hypothesis. Now, I need to remind you, this is not the same thing as accepting the null hypothesis. This means you can't reject it. Conventionally, people use values of alpha as 0.01 or 0.05. You'll notice the choice of notation and the choice of values should be reminiscent of what we use for confidence intervals, the significance level. They're the same because there's a direct link between confidence intervals and p-values hypothesis testing. But why that should be the case here, why people use 5% or 1%, well, 5% would mean that, the probability of rejecting H null when it is indeed true is no greater than 1 out of 20 cases. Like, you'd be willing to be wrong about 5% of the time. Or, if you need more certainty, about 1% of the time. But these are conventions. Why not 10%? Why not 15%? Why not 20%? It depends on the situation. As I've mentioned, there's a bit of a movement afoot right now to sort of like bypass p-values as not being useful bits of information. They're not useful when people don't use them the way they should be used. When people give them more meaning, when people imbue them with more meanings than they truly have. If you're interested in learning a little bit more about this, may I suggest this thread on Twitter by Kareem Carr. Basically explains a little bit what p-values are, how they work, and why sometimes they do not work. So you might want to take a